Good afternoon, everyone. Today is the third lecture of the series, and we are going to start with another topic, which is Pointing vector. This Pointing vector is a mathematical quantity denoted by S, and mathematically it is given by as the cross product of electric field intensity and the magnetizing field intensity. So the cross product of these two terms gives Pointing vector. So I will write it down that the Pointing vector is given by the cross product cross vector product of electric field intensity and this H is also sometimes referred as magnetizing force. So I will write it down as the cross product of electric field intensity and magnetizing force. The magnitude of this vector S is given by as E and H are always perpendicular to each other, so I can expand them in this form, and I will get S as the product of magnitudes of E and H. It can be easily observed that the direction of S vector is always perpendicular to the electric vector and magnetic vector H. Hence, this S vector is in same direction as the velocity of EM wave. As in the previous class, we have proved that the velocity of an EM wave is perpendicular to the plane containing E vector and H vector. So this S vector is always in same direction as that of velocity of EM wave. So today we are going to derive the expression for this Pointing vector and explain its significance. So let us start. So first of all, I can write the energy density corresponding to electric field and magnetic field. So the energy density corresponding to electric field can be written as half epsilon 0 E square. This is represented by UE. UE stands for energy density of electric field. Similarly, I can write energy density of magnetic field. So that is given by half mu 0 H square, which can be written as UH. So if I am going to calculate the energy density corresponding to electric and magnetic field both. So energy density of electromagnetic field is given by the sum of the energy density of electric field and the energy density of magnetic field. So we are going to add both of them. So this we denote as UEM, electromagnetic field. I will call this as equation 1. So I will proceed with that equation 1 over the next page. So let us consider a volume V of an electromagnetic field, then we can calculate the total energy. So this total energy, I am denoting it with capital U. EM is electromagnetic energy, is given by integration of this U EM times dV. So over any volume V, if you integrate the energy density, you are going to get the total energy. So I will use the value of U, energy density of electromagnetic field, from the previous equation number 1. So from this equation number 1, we can get the value of energy density of electromagnetic field. So over this volume V, we are going to integrate. This is half epsilon 0 E square plus half mu 0 H square into dV. So this side we are having the electromagnetic energy. So we can calculate what is the rate of flow of this energy. So the rate of flow of this electromagnetic energy is simply given by dW by dt. This is rate of work done. So you can call it rate of work done or rate of flow of electromagnetic energy from the volume, whatever volume you have considered from that volume. So I will differentiate this equation on the right hand side, d by dt over any volume V, and the remaining term remains the same. So this d by dt can be taken inside this integral. So I will move that d by dt inside the integral. So it will be V0 d by dt over the entire energy. So the terms can be differentiated with respect to time. So it will lead to integration over the volume epsilon 0 del E by del T into E. Similarly, this can be written as mu 0 del H by del T into H over the volume. So now we are in position to put the values of this del E by del T and del H by del T from the Maxwell equations. So I can use the Maxwell equations. According to them, epsilon 0 del E by del T is equal to curl of H and minus mu 0 del H by del T is equal to curl of E. So I can use equation 3 and 4 in equation 2. So using equation 3 and 4 in equation 2. I will do that over the next page. So upon using the value of dE by dt and dH by dt, equation 2 can be written in this form. So this term H curl E minus E curl H, according to our identity, can be written as divergence of E cross H. Along with a negative sign. So in this equation, this term, which is E cross H, we denote it with S, and this S is nothing but your pointing vector. So according to this change, the equation can now be written as now we can use Gauss divergence theorem according to which the flux of this S over any surface can be written as divergence S dot dV. So as the right hand side of these equations are same, I should call them 4 and 5, as already I have taken equations 3 and 4. So these are equation 5 and 6. So I can take that the right hand side of this equation 5 and 6 are same, so I can equate the left hand side. So from equations 5 and 6, I can say that dW by dt, which is the rate of flow of energy, is negative of S dot ds over any surface. So this is our concluding equation. We call it as equation number 7, and now we can see that what is the significance of this equation. So the first conclusion that can be drawn from this equation is that the vector S, which is given by E cross H, measures the rate of flow of electromagnetic energy per unit area. You can also call this rate of flow of electromagnetic energy per unit area. You can also call it flux of power per unit area. and this quantity, which is flux per unit area, you call it this as S, and this S is given by E cross H. So this quantity we name as Poynting vector. So I will write the further conclusions on the next page. The negative sign signifies that these EM waves carry electromagnetic energy with them, and in the direction of propagation of EM wave. So this is the solid conclusion that we have got, that an electromagnetic wave carry energy. So with this, we are done with this topic, and the next topic that we are going to start are the Maxwell equations in different medium. So we are going to consider 3 different medium, and we see that how these Maxwell equations modifies in the 3 different medium. So the first medium that we are going to take is free space. Although we have already discussed the Maxwell equations in free space in the previous class, yet for completion we will take them today as well. So when I say that we are discussing about this free space, then the various parameters are going to change. The first one is that this epsilon is given by epsilon 0 epsilon r, this mu is given by mu 0 mu r. So for free space, I can say that this mu r and epsilon r will be 1. So epsilon will be equal to epsilon 0 and mu will be equal to mu 0. Further, the free spaces, as I discussed in the previous class, this free space is non-conducting. Non-conducting means sigma equals to 0 and there is no free charge density. No free charge density implies a rho equals to 0. So you make the above mentioned changes in the Maxwell equations and you will get the first equation as divergence E is equal to 0. The second equation as divergence H equals to 0. The third equation as curl E is equal to minus mu 0 del H by del D, and fourth and last equation as curl H is equal to epsilon 0 del E by del D. So these are the 4 set of equations which are there considering free space, or you can say vacuum. So in vacuum, the Maxwell equations are of this form. So let us now change the medium and take another medium which is dielectric. So next we are going to start with the Maxwell equations but in dielectric medium. So when we say that the medium is dielectric, we mean to say that the medium is non-conducting. As you know that the dielectric are non-conducting insulators. So when we say that the medium is dielectric, we mean to say that the medium is non-conducting. So further, let us apply certain changes, which are that there is no free charge density. No charge density. Further, the medium is non-conducting, so sigma will be 0. This mu in this case can be written as mu 0 into mu r, and epsilon can be written as epsilon 0 into epsilon r. In this case, this mu r and epsilon r are not equal to 1, as we have replaced epsilon r and mu r equals to 1 in the free space medium. But now it is not the case. So the Maxwell equations for this dielectric medium can be written as divergence E equals to 0, divergence H equals to 0, curl of E is equal to minus mu del H by del T, and curl of H is equal to epsilon del E divided by del T. So these are the equations, these are the form of Maxwell equations for a medium which is dielectric, or you can say non-conducting. So for a non-conducting medium, for a dielectric medium, the equations are of this form. So let us take the third and last case, which is a conducting medium. So when we say that the medium is conducting, it means now sigma is not equal to 0. The electrical conductivity of the medium is now not equal to 0. Further, inside the conductor, still this rho is equal to 0, as no free charge can reside inside the conductor. This is the theorem in electrostatics. You must have studied it, that within a conductor no charge can stay in the rest situation. So in the light of this change, the sigma is not equal to 0 and this rho equals to 0. The Maxwell equations takes the different form. So now in the light of these changes, the Maxwell equations are this curl H is now slightly changed, and now we have a term which is not there in the previous equations. So this term, which is otherwise 0, in the case of conducting medium, this term is non-zero. So these are your Maxwell equations for a medium which is conductive. So for a conducting medium, the Maxwell equations are of this form. So with this, we have completed this series of 3 lectures in which we have completed mainly 3 topics. The introduction class, which deals with Maxwell equations. In the second class, in which we proved the transverse nature of EM wave and the propagation of EM waves in the free space. In the third and last class, we discuss that these waves carry energy with them, and that is being characterized by the term Poynting vector. And at last, we have discussed the form of these Maxwell equations in different media. That is all. Thank you so much.